Okay, welcome back. Um, Quick aside from, or continuing what was from the last video, I forgot to mention that intermolecular bonds, uh, like lattices, work differently when the substance is in different states of matter. For example, a solid is fully the lattice. So, like if I had my lattice and this was like a single unit of it, it'd be like the tetrahedral. If all of these were like molecules, and it just expanded out infinitely, that would be a solid because it is fully rigid, it is fully formed, and is exactly how it wants to be. However, when you add energy to it, all these little bonds are going to start breaking apart. And what's going to happen is the molecules are not going to be organized. And the state in which it becomes a gas is when there are no more bonds. The molecules are not being held together by any force whatsoever, besides gravity, and they're just there. The in-between state is a liquid. A liquid will have some, but not all. Actually, there are different states of matter. Think about ice. Ice is a liquid, but when it turns into a solid, or I mean, water is a liquid, but when it turns into ice, the solid, what it does is it freezes up and solidifies into a structure. That's why snowflakes are so cool, because it's the structure that formed around the ice. So, moving on, let's talk about band theory. This is a slightly different topic, but it jumps into conductivity. So, there do exist insulators and conductors. Insulators repel heat. Well, they don't repel heat, actually. Uh, I take that back. But they're very good at soaking up heat. While conductors are like, they'll take in the heat and it's no problem. So this is actually like the amount of energy it takes, or band theory discusses the amount of energy it takes to get an electron out of its home shell, the valence shell, into the outer shell, the ghost shell is what I call it. It's like when you have an atom, I'm going to draw this. When you have an atom, let's say hydrogen, just for simplicity, it's going to have one valence electron in its outermost shell. But if you add heat to it, there is a shell right here, which technically is not part of the atom, but it is an energy level anyways. So if I add heat and more, the electron is going to jump out and go up there. And there is a certain amount of energy I have to pour into this atom to get the electron to do that, to enter an excited state. Once an electron is out of its comfort zone, it will be able to participate in conduction and in other stuff, or essentially like the transferring of energy. Now, you can actually put this on a graph, or not really a graph, just like a thing. So, this is going to be more like a bar graph where it just goes up. So, I have threshold 1, threshold 2, threshold 3, just for simplicity's sake again. Under threshold 1 is the region in which the electrons are in their ground state. Like, this is the amount of energy they have, and so I'm just going to label this energy. And there's nothing going on the x-axis. It's just a rise. So this is the amount of energy a ground state will have. I'm going to change color. A ground state will always have less energy. Now, above it, you have a region, which is this. All of this above it is the amount of energy I can add to it. So like if I add, let's say like 5 units, all of a sudden, boom, that's how much energy it could have. If I go up here, boom, that's how much energy it has. But what this graph measures is not how much energy the atom has, but how much it requires to jump into the next shell, to jump into that range where it can participate in conductivity and stuff. So, metals, as you already know, are very good conductors, but this is why. It's because the amount of energy required to get them to jump is pretty low. You barely have to give them energy for them to do anything. Like you give it a bit of energy and the electron's like, oh boy, I'm heading out. So this location is, or like everything above here is like conductivity. Now there is a difference between different substances. I'm gonna write metals. Actually, I'm gonna put it inside the box. So notice there's no gap in between the ground state and the amount of energy they need to become conductive. That changes when we get into semiconductors. So let's pretend this is another one, but it's for insulators. So insulators need to have a lot of energy put into them before they start participating. They'll be like, no, 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 give me a ton more energy and then I will start helping you. So their energy like range, like the range of energy they need to have is going to be up here. So if I haven't, like, let's say an oxygen atom in ground state, if I want it to be conductive, I need to put in all of this energy until it gets to here. This point of having energy, an electron will be like, yeah, man, I'll head up. I'll do it. And he heads out. But not before he has enough energy to do it. There's draw an arrow right there. And compare and contrast with metals, it's all the way up there. So now there is a third one, a third type of element. I think you know what it is. It's the semiconductor. The semiconductor is exactly what you are probably thinking it is. It's in between. A semiconductor does not need as much energy as an insulator does to conduct anything, but it is not instant like a metal. This is why semiconductors are so useful in computers, because you can control how much energy goes into one and flows through it. Very interesting. Anyways, this is the gap, the band gap. Let me check and see if there's actually some terminology for that. Uh, um, Band gap. Yep, it's just band gap. That's what it's called. It's called the band gap. Uh, yeah, the band gap. And and yeah, so this band is called the valence band because it's where the valence electrons hang out. And these are called the conduction bands, I think. Yeah, the conduction bands. I'm not looking at ChatGPT or the slides or anything. I'm actually looking at the homework combined with my own notes. So the conduction band. So why is it called a band? This is actually just saying shell, but because there's a bunch of different atoms and a bunch of other random stuff, it's more like a range, a little spectrum. So we say band instead of shell. It's as difficult as that. Not too bad. So now that we've gotten into there, we can talk about doping. So doping is the act of adding an element to a collection of a substance in order to move these gaps. So let's say I have a semiconductor, I don't know, like arsenic. Arsenic, we can pretend is right here, and I want it to be more conductive. I want it to do it faster. So I'm going to take a bit of another element and I'm going to add it to arsenic. And the arsenic band is going to move down just a bit. Let's say it goes from there to end up right here. Actually, that's really tall. It ends up right here. I've added a substance as an alloy, just like a tiny bit, like a minuscule amount comparatively, to make it lower, so I only need to add a little bit less energy to get it to conduct. That's also why semiconductors are cool. Anyways, what is this? This is called doping. I don't know why it's called that, but it's weird. And there are two types of doping. Like the active doping is adding electrons, or no, is adding an element that has certain properties, Uh, but there's two types of that. So if an element, like the the host substance, I could say, has a certain amount of electrons or valence electrons, the first way that you can get it to become more conductive is to add an n-type semiconductor, which will have more electrons in its valence shell than the semiconductor base. So let's say I have arsenic. Arsenic only has 5 valence electrons. So if I want it to have more conductivity, you could say, I can add an element that has more valence electrons to it. For example, I can add a tiny bit of selenium. What selenium will do is it will take its extra valence electrons and it'll be like, hey, I have these to share. This is called n-type doping because the total amount of valence electrons are to share increases. Review the homework in my notes, see if I said that right. Yep. The dopant in an n-type semiconductor will have more electrons in its valence shell than the semiconductor base. This leaves the doped material with a net negative charge which can be promoted into the conductance band. That's where, okay, I'm reading off of that. That's why it's called n-type, because it's negative. It's adding more electrons, so it's an n-type. The other type is p-type, where you add in one that has fewer electrons. For example, like germanium. Germanium is on the group before arsenic, if I remember correctly. So it will have like 4 valence electrons, I'm pretty sure. What the heck? Don't cut my nails. What will happen is in all the bonds, it'll essentially create a hole in the arsenic, and it'll want to bring on more electrons. That's why it's called p doping. Um, it's a net positive gain. Uh, yeah, so let's see what my notes have to say about that. Doping. Oh, it's gone. Okay, yeah, I dope pure germanium with arsenic is n-type doping because I'm adding a small amount of arsenic to germanium. However, if I dope pure arsenic with germanium, it is a p-type doping because I'm adding germanium to arsenic. So you can see how it goes both ways. It's just like I have an element, a bunch of it, and if the element I add to it as a dopant has more or less, it's going to result in p-type or n-type doping. Both of them increase the conductivity of your host element, which is good. Okay, what's next? I think that might be it for doping. Um, let's do a math problem. Just an example from the homework. Um, so this isn't really like a math concept, but it can be. So the question says, suppose a device is using 18.6 milligram sample of silicon that is doped with 1e negative 5% phosphorus. So 1e negative 5 phosphorus as a dopant, and that's percent, and it's by mass. So it's easy. And so the question is, how many phosphorus atoms are in the sample? Well, all we have to do is find the percentage. 18.6 milligrams. Well, first we have to convert that to moles. So what is the 1e negative 5% of 18.6? 18.6 out of 100, I think this will work, is equal to 1e negative 5 out of how much percent? Does that work? Oh no. Yeah, so this is the percentage. I need math. What is 0.000%? Frick. I've lost the ability to do math. Okay, I think I figured it out. I was getting there. So if I have 18.6 milligrams, 18.6, I'm going to just convert this into grams real quick. 0.0816. That is, out of however much is 100%, is going to be 1e negative 5 out of 100. So what is, if I divide 0.0186 into that many parts, what is a single one? I'm going to end up with, let's get my calculator out. My brain cannot do this math right now. 0.0186 times 10 to the negative 5. 100 is going to 1.86 e negative 9. 1.86 e negative 9. And from there, it is, that's how many grams there are. So we have grams. Now what we can do is, that's how many grams of phosphorus there are, so we can convert to moles. Phosphorus has a molar mass, or molar mass of 30.97, so we'll just divide that by 30.97, 3762. Dimensional analysis, let's go. 1 gram is, after that, now that we're in moles, we can convert to atoms by multiplying by 6.022 E23 particles per 1 mole. Easy. And that'll just get us how many atoms there are. So, divide, then multiply by 6.022 e to the 23, and we get, I got 3.6162. Double check that. Yep, 3.62 E13. I do not know why I had such a hard time converting to whatever they are, convert to the thing. It's like 1 E negative 5% of that is E negative 9. I have to remember that for the test. Undoubtedly, that is going to be on the test. Okay, so that's dopants. And yeah, that's it. Thanks for watching. Have a great night.